Welcome. In this video I'll go through the two fluid equations and introduce in a bit more detail how these equations are derived from the Boltzmann equation. So if you haven't seen lecture 5 before, where I derived some of the equations of ideal MHD from the Boltzmann equation, then that would be useful to go through. This lecture I'll go through I won't go through much of the actual detailed calculations because you'll find that earlier. I'll just look at the equations and show you what they mean, and try and show how you get the moments of the collision operator come into the equations, and then discuss how the closure works. So starting from the Boltzmann equation, where here f is the distribution function, which is in general some function of time, 3 dimensions of space, and 3 dimensions of velocity. And so here we have the change in time, the advection in space, so this v is a coordinate, but it's the velocity that the particles are moving in space, and this is the force which accelerates them, and so this is essentially the acceleration in each of the 3 directions. And then here this is the collision operator, and here this combines essentially collisions with lots of other species. So if we label say this S is a species, then this C is for a particular species. This could be ions or electrons, for example. So S is like could be electrons or ions. You have multiple ion species, for example, and this S, this collision operator is actually a sum over the collisions with all the other species. So it's the sum over other species S prime of the collisions between species S and species S prime, and that depends on the distribution function of both, so f of S and f of S prime. And in general this could be quite a complicated expression. Usually this is assumed to be bilinear, so we assume that this function here is linear in f of S and linear in f of S prime. And then from this Boltzmann equation we then calculate equations for density, velocity and pressure or energy. And so for example the density, which is some function of time and space, we get from integrating the distribution function f, we get time x and velocity v, and we integrate that over all 3 velocities, and this gives us a function of time and space only, because we integrate out this one here. And then we can take higher moments, for example in u, here's the fluid speed, fluid velocity, again is time and space, and this is an integral of the velocity times f, t, x and v, again integrated over all 3 velocity dimensions. And so we can keep going to higher and higher dimensions, and so you have integrals with v to some power, f of t, x and v. And this is a moment hierarchy, it's called, so we're taking moments of the distribution function. And the problem we've seen a few times already is that every time we multiply this equation through by a factor of v, so if you want to calculate the density equation, for example, you just integrate this equation here, and you have a term here which is a velocity times f, and this of course gives you the advection, because this gives you a term involving n and u, the flow speed. And then when you multiply through by v here to calculate this equation, so you need to work out the time derivative of v times f, so you multiply this through by v. Here you have a v squared, and a v squared gives you v cubed, and so this term here, this advection term, means every equation depends on the next equation, and so you need to close the set of equations somehow. So and there are various ways that this is done. Well, so the equations we get out, so the first few are the density equation, so we have dn by dt gives us a density evolution, then we have the advection term, so we have advection of particles, and that's just equals 0 if there are no sources in the sinks, and that of course means that in our collision operator here we're just saying that the integral of c over all velocities is 0. So i.e. we have the integral of c f dv So collisions don't result in any appearance of new particles. In general, you might have atomic reactions, which might create different kinds of species if you have collisions. But here, at least, we're neglecting that. Then the next one is the momentum equation, so you end up with an NU. So this is the momentum equation. So we have the mass of the species, we have the flow, velocity times the density, so it's basically like momentum. Here we have the pressure tensor. So this can be a scalar in some simple cases like ideal MHD, but more generally it's a tensor. And then we have the charge Q. This is the charge. There's another Q used later for heat flux, but this is the charge of the particle. And then here we have the Lorentz force, and then this is the friction. And so this is the integral of C F times V. Then we've got an M factor in here as well, so this has got a mass integrated over V. So this is the force due to collisions on the species. And because this collision is made up of lots of individual collisions with different species, we can write this as the sum. So R is the sum over all other species. So we have the mass, then we have the collision between S and S prime. So F of S and F of S prime times V dV. And of course, the momentum must be conserved. And so for any pair of collisions between species S and S prime, we must have that the mass, this is the mass of species S, times this collision, so it's S and S prime, so the force on species S due to collisions with S prime must be equal and opposite to the force on S prime due to species S. So that's just conservation of momentum. Now the pressure tensor, we can just write, so P is again a higher order moment, so this can be written in several different ways, but this is just the mass of the species. And now it's convenient to write this in terms of another velocity W, where W is the relative velocity. So W is the velocity of the particle minus the flow velocity. So this is a relative velocity of the particle relative to the fluid, and this is the distribution function. So it's the square of the velocity in the frame of the fluid. This is in 3D at least. This is a 3 by 3 matrix. And the pressure, the scalar pressure, is the diagonal. So if you take the trace of this pressure tensor, so we take the sum of the diagonal, what we end up is 3 times the scalar pressure. So a third of the trace is the scalar pressure. So if you have ideal MHD, for example, the pressure tensor is just this, and then everything else is 0. So this would be like ideal. But in general, these off-diagonal terms are not 0. All these terms can be different, say parallel to the field. So one direction here is along the field, and 2 are across it. So you might have different pressures in the different directions. Now the diagonal terms you can write down just by simplifying this. Essentially this just becomes an omega squared, omega dot omega, and then so if you look at this term, there's an expression for the pressure tensor. So you have here, if you're on diagonal, it just means that these two are just dotted together, so it's omega dot omega, so it's omega squared. this kind of looks a bit like a kinetic energy. So if we make a half m omega squared, this would be the kinetic energy in the frame of the fluid. And so this is the internal energy. And if we take the trace, we get 3 times the internal energy. And so we can just write down, so here we have, this is half mw squared, so the kinetic energy in the frame of the fluid. This is the pressure, and this is of course just the internal energy. So what people do is write the 9 component pressure tensor in terms of this scalar pressure plus the extra components, which are the viscosity tensor. And so write down that the pressure tensor is the scalar pressure times the identity matrix, so just ones along the diagonal, plus equal pi, which is capital Pi, which is the viscosity. And there's also a tensor, so I'll just put it under here. These are all tensors. So you can work out an equation for how this varies, how the scalar pressure varies, by just taking moments of the distribution function of Boltzmann's equation. And so we need to work out how half mw squared times f varies. So just multiply this equation through by half mw squared and then integrate. As usual, this term gives higher order terms, so higher order moments. In this case, a heat flux. And then we can write down, using this, we can just write down an expression for scalar pressure, i.e. this moment here, this 3/2 times p half mw squared. So multiply through Boltzmann's equation by half mw squared and then integrate over all velocity. So here several terms have appeared. So this is the part of the advection terms. This is the flow velocity just carrying pressure around. This is a dyad. So this means a sort of double contraction over this tensor, and this here is the tensor. If you prefer the tensor notation, this you write as you have 2 components, and then you have a gradient of u with respect to u components and gradient components. So here you have u beta and partial sort of component x alpha. So you see here we have 2 indices, and then here we have 2 as well. So this is the double contraction of this u and this gradient. So this q, this here is the heat flux. So there was a q earlier, which is a scalar, which is the charge. This q is a vector, and it's the heat flux. And we can write it down. It's the third moment. So we now need a higher order moment of the Boltzmann equation. And then it's W here, this is the energy or heat exchange with other species. And so again, we can write down that W is the sum over all other species, so S prime. Here we give this WS as the species S, so here we call this species WS. There's the sum over all the other species of a heat exchange between S and S prime, which again depends on F, S and F, S prime. So each one of these is just a moment of the collision operator. So this is a sum over S prime of a half m W squared times the collision operator between S and S prime, the 2 species, Fs and Fs prime. So this is the second moment of the collision operator, summed over all other species. And now, because we have also energy conservation between 2 species, this exchange of energy W between S and S prime must be balanced by a flow of energy between S prime and S. But there are 2 sources of energy here. So one is this kind of internal energy, is the heat, and the other is the kinetic energy, which is in this momentum equation. So this friction between 2 species can also transfer energy between them. And so if you have energy conservation, then we must take that into account. And so what this means is that the transfer energy from S prime to S, so Ws, so the heat into species S due to species S prime, plus the kinetic energy. So we have the velocity of species S minus the velocity of species S prime, So that should be a u's of my flow velocities, dotted with the friction. So it's basically a force times a distance, and this is the friction between species S and S prime. That should be equal to minus W S prime S. And this is essentially the work done on species S due to S prime must be the same as the work done opposite to the work done by S prime by S. And this takes into account both the internal energies and the work, the kinetic energy. So this is the friction. Okay, so the main problem with this model, as with all fluid models, is it's still incomplete. So we still need to know what this term is. So we need to find some kind of equation for what is the heat flux. We need some kind of equation for what this W, these W's, so these moments of the collision operators are, and something for some way of working out what this viscosity tensor is. So there are at least these terms to be calculated. So the viscosity tensor, the heat flux, and these collision operator terms. So we have the higher order moments, the viscous tensor and the heat flux, and we have the collision operator terms. So R for the friction and W for the heat flux or heat exchange. Now there are at least two different ways of calculating these. One is just through truncation. So essentially you just set these to 0. So that's the approach ideal MHD takes, is just set heat flux to 0 so it's adiabatic, and set this viscosity tensor to 0. There are other more systematic ways of doing this, essentially using expansions in small parameters. So Chapman-Enskog is a series or an example of this, where you choose a small parameter, for example the mean free path over the length scales, or the collision frequency and the typical frequencies of interest, and that allows you to expand the distribution functions in a series of powers, and then solve for them. And this gives a way of closing these equations. So we'll discuss that in a future video.